name is Clemens, I'm the CTO of Percival, and I'm the technical project lead of the first OpenMATERIAL 3D standardization project at ASAM. In this video, I'm going to give you a brief introduction into the standard. You're probably familiar with some of the other OpenX standards at ASAM. So let's start there. There's ASAM OpenDRIVE. It standardizes the format on how to store and read road networks. So it answers the question where we're driving. OpenSCENARIO, also a data format, contains every dynamic element of a scenario. So it answers the question, what are the dynamic elements doing and what's happening in a certain scenario. ASAM Open Simulation Interface, or OSI in short, is an interface standard. And with it, you can transfer data between different models in a co-simulation. And you can also use it to store simulation outcomes. So it answers the question how to transmit data and information between models. But one thing is missing. There's no standard for how the environment actually looks like. And that's exactly what OpenMATERIAL is about. And the question is not only what does the environment look like to a human observer, but especially what it looks like to perception sensors. And this is what we were targeting in this project, and this is what the standard is all about. And what something looks like has basically two components. So you have the 3D geometry, so you have a 3D asset, and then you have physical material properties assigned to this geometry. We go a little bit further because we don't only have rigid bodies, they have a certain structure, you want to do animations, and that's why we defined a hierarchy for moving parts. We need coordinate systems that are clear and clearly defined to achieve the end goal, which is to do physically accurate perception sensor simulation using all the other ASAM standards, and now with the missing link, OpenMATERIAL 3D, we can have the full package using ASAM standards. I don't want to go on and showing one slide after another. I think the best way to show you what the standard is about is going into the documentation. Because you're invited to follow along, opening up the documentation yourself and go deeper into the topic after this brief introduction. The entire development of the standard was completely open. We did it all openly on GitHub. So everything you need to get into the standard, you can find on GitHub. It starts with the GitHub main page. You can see the URL right here. So it's at the ASAM EV organization. And then we have OpenMATERIAL 3D as a repository. And the first contact point should be the documentation page. You can find the link here on the right side. And if you click on it, it will bring you right to the documentation of OpenMATERIAL 3D in this first version 1.0. Let's jump right into the introduction. OpenMATERIAL 3D has two main parts. As I said in the motivation, 3D assets mainly consist of the geometry and materials. And in terms of the standard, it sometimes makes sense to only use one part of it. So if you already have a geometry description in your simulation tool and just want to add the material side of it to it, you can do so, and you can use the material part. Or the other way around, you're mainly interested in the geometry, you want to standardize coordinate systems and animations, you can use the geometry part without the material part. But for full compliance to the OpenMATERIAL 3D standard, you can use both, and they work in harmony with each other perfectly. So how is the standard structured? Right in the introduction, there's a nice overview page. And we have different components, different file formats that all work together in this standard. We didn't want to reinvent the wheel. So there's a lot of 3D data formats and 3D model exchange formats already out there. So instead of replacing them, we actually want to utilize them and build an ecosystem around them. So for OpenMaterial 3D, we have 3 data formats that are officially supported, and that's FBX, GLTF, and USD. And that's the typical 3D models that many of you are already used to. But there are some things missing from these existing file formats. The first thing is metadata. Alongside each 3D model file, we define an asset file with the same file name or different file ending. This is a JSON file and has the file ending XOMA for ASAM OpenX standard OpenMaterial asset file. And in this asset file, we define metadata. So you can have information like a description, who's the author, what are copyright information, license informations, and so on for this asset. Then the question is, okay, if I have my 3D model, I have metadata, but how do I get material data assigned to it? And that works with a mapping file. That's linked in the asset file. You can see that here. So there's some material mapping, that's the URI, to another file format, that's the material mapping file. It's another JSON format, XOMM for OpenX standard OpenMaterial mapping. And this mapping file contains a map of names of materials and material property files. So you can see up here in the 3D data file, you have contained materials that contain materials for typical rendering workflows, for example, a physically based rendering workflow, or others, doesn't matter. The only thing we need is the name. So you see here we have a material called asphalt, and then in the mapping file we can say, hey, every material that's called asphalt has a corresponding OpenMaterial property file. I will get to that in a minute. But sometimes you need a little bit more detail. And that's what textures are for. In typical 3D modeling, you don't model out every detail in geometry, you use textures. For example, here you would use the rough outline of the stop sign and then attach a texture with this red and white image here. And we wanted to do something similar in OpenMaterial to give the possibility to assign physical material properties on a pixel level in a texture. And that's why we have texture assignment. So for each visual, purely visual texture in a 3D model, you can assign an OpenMaterial assignment texture. So that's just another texture file. It can be any typical texture format like JPEG or PNG. And this has a color code in it. And you see an excerpt or an example down here. These are not visual colors. Those are merely codes. And now you can define everything that has the RGB code 00255 points to a material property file, steel red. And for 02550, you point to steel white. So you can have an assignment by material names or a more detailed assignment with dedicated OpenMaterial 3D textures. Now, what are these files about? We have the mapping, but now let's dig a little bit deeper into how to actually define material properties. Everything in red here is part of the geometry chapter, and now we're basically crossing the line over to the other chapter, that's the material chapter, and that contains everything you see here in blue. From the mapping file, we have assignments to OpenMaterial property files. And as you guessed it, these files contain OpenMaterial properties. And these properties are physical properties on the one hand, For example, a density of a material or a surface roughness of a material, all defined in physical units. But sometimes we have more complex properties, properties that depend on different parameters. For example, the wavelength of the sensor looking at it, or the temperature or the humidity. And that's why we have defined separate lookup tables. So from the material property file, you can link lookup table files. They're called XMPT for OpenX standard Open Material Property Lookup Table. And some examples of these are an index of refraction or permeability, permittivity. So properties you need for simulating infrared sensors like a LiDAR or a radar sensor. But aside from physical properties, sometimes you have measurements of reflectance, or you have separate models for the reflectance of a material that are calculated offline. So that's why we have also the opportunity to define BRDFs, so bidirectional reflectance distribution functions. They're used a lot in computer graphics. They can either be used, they can either be calculated online during the simulation, or in this case be stored as a lookup table coming from a measurement or an offline calculation. And this is also one possibility. So this gives you a brief introduction in how Open Material is structured and how all these parts play together. One thing I have not talked about, and that's the hierarchy and structure of 3D models and how to use them for animation. I briefly talked about this at the beginning of this video. So let's actually go down into the chapters and explore that. So here on the left side, we're currently in the introduction. Feel free to read through that. We also have a whole section of how Open Material 3D plays together with the other ASAM OpenX standards. But now let's go into the chapters. We have the geometry chapter here and the material chapter here. And for the geometry chapter, for once we have schema files for all the JSON formats that I just showed you. So you can look at the asset schema or the material mapping file schema. Look at that, but let's actually take a couple of minutes to dive deeper into object hierarchies. Because we have defined in the general section, we have defined coordinate systems, so the basic layout of an object, where's the origin of an object, and these kinds of definitions, what dimensions to use. And then we have object class specific hierarchies. Let's take the vehicle as an example. We go to the vehicle chapter. You will see an extensive hierarchy of how a 3D model of a vehicle should be built up. And we have done this in groups. We call them groups, and some tools, they're called empty nodes or pivot nodes. And these define coordinate systems. And with this definition, I'm going to give you one specific example, and that's the example of the wheels. So if we go to the group wheel, you will find a nice image here that first defines where the coordinate origin of a wheel should be, what's defined as a wheel, and we have different subgroups because on a wheel, if you want to do animation, and the car is driving, the tires will rotate, but other parts of the wheel assembly will not. For example, the brake calipers, they will follow the steering motion, but they will not follow the rotation. So that's, just as an example, we've separated them. We have one group for parts that follow the steering motion and one group for parts that follow the steering and rotating. And this enables a simulation model or a simulation tool to simply import an ASAM OpenMATERIAL 3D compliant 3D asset like a vehicle, and you instantly know where's the origin, where are the wheels, how can I manipulate the parts in my simulation, and that's for all the parts. For example, also the doors. We have the doors defined with their hinges, so the simulator directly knows if I want to open a door, I know exactly which part of the mesh belongs to the door, and I can manipulate it. We have the same for other object types, so we've also defined the skeleton for humans. So you can just drag and drop a human into a simulation tool or sensor model or a traffic participant model that supports OpenMaterial 3D, and you can directly manipulate it and move it. And the same for the environment. We've defined coordinate systems for vegetation, for buildings, for the road network, for traffic signs, traffic lights, and so on, so they can directly be used in the simulation. To wrap this up, one brief look also in the material chapter. Here, the same for every JSON format we have defined. We have a schema here. So feel free to have a look at it. Here, for example, you see all the material properties that we have: surface roughness, emissivity, elasticity, density, and so on, that the standard in this version 1.0 offers. One last thing to mention, a standard, especially since we have a lot of these different file formats and how they work together, it takes some time to work into the standard, read through the documentation, and implement all of this and use it. And to make it a little bit simpler, there's a rather new initiative at ASAM that's the quality checker framework. And for that, we have defined certain rules that OpenMaterial 3D compliant materials or 3D assets need to follow. And yeah, that's a nice addition because you have very distinct rules. There's also a separate checker bundle that can be used to automatically check if a 3D asset complies to these rules, to just make it a little bit easier to have standard compliance for your tools, for your 3D environments, or generally 3D object and 3D assets. This wraps up this brief introduction into the new ASAM OpenMaterial 3D standard. Feel free to browse through the documentation. We also have on the GitHub repository a lot of examples for every object class, for the material mapping and everything you need. So basically every aspect of the standard we have examples for. So feel free to explore, feel free to participate on GitHub, write issues, and have fun with this new standard.